said, hey, you, let's do some diffie-Q. If something's looking blurry, then we'll bring it into view. I said, hey, you.
Check it out.
Welcome. Let's do some diffie-Qs. Today we're going to talk about the Laplace and inverse Laplace transform and how they relate to one another. We'll start with the Laplace cycle. Here's a diagram representing the Laplace cycle. In order to solve differential equations using the Laplace transform, we will use this cycle. We'll start with a differential equation of this form that is linear constant coefficient, not necessarily homogeneous. To it, we will apply the Laplace transform, giving us that we have the Laplace transform on both sides. We'll restructure this algebraically so that we end up with the Laplace transform of x is equal to the Laplace of some function g of t. Then, by applying the inverse Laplace transform, we'll end up with x is equal to g of t. So to reiterate, we start with some differential equation with a linear operator L applied to x is equal to some f of t. We apply Laplace transform to both sides of that differential equation. We then do some algebraic restructuring until we get the Laplace transform of x is equal to some Laplace transform of a g of t. Then applying the inverse Laplace transform, we essentially peel away Laplace and are left with x and g of t. So in order to solve this differential equation, whose solution would be this, we pass from the t space represented in blue here over to the s space represented in orange. We do some algebra in orange and then apply the inverse Laplace transform to move back into the t space. It would be nice if we could go from here to here, but that's not always possible. So this is a technique where we sort of work around indirectly in this cycle and end up with our solution. It may seem roundabout, but it allows us to solve differential equations that we might not be able to otherwise. So let's first talk about what a linear differential operator is. So a linear differential operator, it's a function that takes another function, so it's a function of functions, that takes a function that's sufficiently differentiable and it turns it into some other function. So it maps differentiable functions to other functions, and it has a very nice property. The property is linearity. So the differential operator is essentially this part, the linear part of this term is this part here. Now, if we have two real numbers, a and b, and you have two functions, f and g, living in this space, the domain space, then when you apply the linear differential operator, if you apply it to a sum like this, notice what happens, that we can essentially split it apart. We can, one, pull out constants, a, so that can come outside, b can also come outside, and also we can split it across addition. So we can turn AF plus BG into A times the L of F plus B times L of G. So we're able to completely deconstruct this and write this expression like so. This is an essential property that we need to be able to use this Laplace transform cycle. And it's true that both Laplace and inverse Laplace are both linear differential operators. One of the key points here is that they both have this property. You can split across addition, so to speak, and you can pull out constants. Notice the constants are inside the argument here, and then here they're outside. Now let's see what it's like just to simply compute an inverse Laplace transform. If we suppose that there's a function f of t, and we apply Laplace transform to it to get capital F of s, then applying the inverse Laplace transform to both sides, we see that there's the opportunity for the inverse Laplace and Laplace to cancel, which they do, leaving us with just f of t. Meanwhile, there was nothing to cancel on the right-hand side, so we end up with the inverse Laplace of this function, capital F of s. So the key here is, if we want to find the inverse Laplace transform of some function, we have to know what function would we start with, take the Laplace to get that function. It's very much like the antiderivative. you have an expression and you want to find the antiderivative, you think, for example, cosine of x, you want to find the antiderivative, you have to ask yourself, what was the function that we differentiated to get cosine of x? Differentiating sine of x gives us cosine of x, so it follows that the antiderivative of cosine is sine, and because of the fact that the derivative of a constant function is 0, we have this plus. It works exactly the same way here with the inverse Laplace transform. Let's now do our first computation. Suppose we want to find the inverse Laplace transform of this expression, s plus 3 divided by s squared plus 4. First, we separate the expression out so that we have s over s squared plus 4 plus 3 over s squared plus 4. From there, we'll note that we can take 2 divided by 2 is 1, and then times 3. So you'll notice 3 halves times 2 is going to be 3, which gives us this. Now the reason we chose to have a 2 up here is because 2 is the square root of 4. That'll come up in a moment, but let's continue where now we use linearity. By linearity, we split across the addition. Notice we went from 1 instance of the inverse Laplace to 2 instances of it. We also then factored out or pulled out the 3 halves. Now I've colored these green for s over s squared plus 4 and blue for 2 over s squared. By checking a Laplace table, or doing it from scratch, but most likely checking a table, what you'll find is that taking the Laplace transform of cosine of 2t gives us s over s squared plus 4. Likewise, taking the Laplace of sine of 2t gives us 2 over s squared. If that's the case, then the inverse Laplace of s over s squared plus 4 should be cosine of 2t. And the inverse Laplace of 2 over s squared plus 4 should be sine of t. And the 3 halves was along for the ride, so it sticks around. We've now computed the inverse Laplace transform of this. Let's look at another computation. Suppose we want to find the inverse Laplace transform of f of t, and we'll call that capital F of s. That f of s in this case is equal to 1 over s plus 1 squared times s minus. Now a caveat here, of course, is that the Laplace transform of lowercase f of t we're taking to the uppercase f of s. With that, what we'll do is we'll rewrite this expression, that is f of s, rewrite it using partial fraction decomposition to write it like so. Notice, since we had a s plus 1 squared, we will get both a over s plus 1 and b over s plus 1 squared. That can be something that's very easy to forget. So as you repeat linear terms, you have to scale up appropriately. If this was s plus 1 cubed, you would have a over s plus 1, b over s plus 1 squared, plus a d over s plus 1 cubed. If this was s plus 1 to the 10th, you would have 10 terms. With that, we can rewrite it algebraically, like so. And now let's start substituting some values of s. Letting s be equal to -1, this expression will simplify down to the following. Then we'll let s be equal to 1, giving us the following for c. And finally, we'll let s be equal to 0. And some more computations give us that a would then be 1 over. Notice that a, b, and c are all present. So indeed, we needed both a and b, 2 different terms. Let's move this to another page. Now what we found is that f of s can be written in this way, where a, b, and c we've determined as follows. Now at this point, we'll apply the inverse Laplace transform to both sides. Notice that we've applied the inverse Laplace transform to this whole expression on the right. Using the fact that the inverse Laplace transform is linear, we're able to rewrite it in the following way. Where notice we have separated this into a sum of 3 inverse Laplace transforms, where we've pulled out each of the constants. Now, taking the inverse Laplace transform of f of s, since the Laplace transform of lowercase f of t is capital F, the inverse Laplace transform capital F of s is simply f of t. And now, nothing will change with the constants, so we can represent those. Checking our Laplace transform table, we'll find that the inverse Laplace transform of s plus 1 be equal to e to the negative. The inverse Laplace transform of 1 over s plus 1 squared will be t e to the negative. And then finally, the inverse Laplace transform of 1 over s minus 1 will simply be e to the. Let's do another computation. Here we want to find the inverse Laplace transform of 1 over s squared plus s plus 2. Now it's not possible to factor this over the real numbers, so we'll set this up and instead we'll complete the square. To do that, what I've done is taken the term in front of the linear. What I've done is taken the factor or coefficient in front of the linear term, the s to the first. That is 1. If you divide 1 by 2, you get a half. Square that number, and you will get 1/4. This is called completing the square. Now I've chosen to break apart 2 into 2 parts, 1/4 and 7/4. Observe that if you add 1/4 to 7/4, you'll get 8/4, and then that is of course 2. Now I've siphoned off a 1/4 here because it is exactly the number that is as I described. Take 1, the coefficient, divide it by 2, and then square it. The reason we've done that is so that we can now take this s squared plus s plus 1/4, and we can factor that. It factors as s plus 1/2 that quantity squared. Now that of course leaves the 7/4 here, and this might make you think of, or vaguely resemble, having a sine or cosine, where we had usually s squared plus something squared, like an 8. Notice we can represent 7/4 as square root of 7 divided by 2 squared. If you square square root of 7 divided by 2, you will get 7. The reason we've written it this way is to fit a form in the Laplace transform table, where we want something squared plus something squared. Notice here, what I've done is I've multiplied and divided by square root of 7 divided by 2. If you multiply 2 divided by square root of 7 times square root of 7 divided by 2, what you will get is 1, and 1 is what we had here. Now we take the inverse Laplace transform of both sides, this expression and the rewritten expression. Because the inverse Laplace transform is linear, we're able to pull out the 2 over root 7. And now we make a note that if this were root 7 divided by 2 all over this quantity, and instead of having s plus 1/2, we just had s itself, so s squared, we would be immediately able to say that this was sine of root 7 over 2 times t. However, we have this shift, s plus 1/2. That shift amounts to, in the end, multiplying by a given expression. So notice that we have sine of square root of 7 divided by 2t, as I mentioned. The constant stays there. But because of this s plus 1/2 shift, what we have is this extra expression. Down here, as I mentioned, if we took the Laplace transform of sine of square root of 7 divided by 2 times t, we would get this, where the only difference between this expression and this expression is, in fact, this s plus 1/2 shift. So we would write this, which is what we would have gotten anyways, but because of the shift, we have this here. I hope you found this video helpful. We'll see you in the next video. To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.